So this will be the first lecture out of chapter 2. So one thing that we cover in this chapter is the basic structure of the atom. So that's what this first lecture will be over, the basic structure of the atom. We'll start with basically Dalton's atomic theory of the atom. So by a scientist named John Dalton. He lived from 1766 to 1844. So that's not that long ago, right? So we have learned basically everything that we know about the atom, the structure of the atom, over the last 200 years. And of course, a lot has been learned over the last 200 years. So all matter is composed of indivisible atoms. An atom retains its identity in a chemical reaction, but not during a nuclear reaction. But we're not going to be talking about nuclear reactions in this chapter or this semester. If you take General Chemistry 2, there's an entire chapter devoted to nuclear reactions. But in chemical reactions, atoms maintain their identity. An element is a type of matter composed of only one kind of atom, and each atom of a given kind has the exact same properties. Okay, so it basically starts with the element symbol, or also called the atomic symbol. So that would be something like this, Ca or O. So if you look at a periodic table, you have all of these atomic symbols. So Ca, of course, is calcium. O is oxygen. So it's usually a 1 or 2 letter notation used to represent an atom of a particular element. So usually it's the first letter or the first 2 letters of the element's name. So F, for example, is fluorine, Br is bromine, but it's not always the first letter or the first 2 letters. For example, chlorine is Cl, so that's the first and third letter, and sodium seems to have no relation at all since it's Na. So where does Na come from? Or potassium is K. There's no K in potassium, so where does Na come from? So so sodium's name comes from its Latin name, or its symbol does, which is natrium. So that's where the Na comes from. So some of the elements' symbols come from their Latin names. Okay, so if you've ever had any chemistry before, then you surely understand the basic structure of the atom. Even if you haven't had any chemistry before, maybe you know the basic structure of the atom, right? Kind of looks like a cell, where you have a nucleus, and then you have what's known as an electron cloud. Right, so what's in the nucleus would be protons, and neutrons are in the nucleus. Those are called nucleons. And electron clouds contain subatomic particles called electrons. So basically 3 types of subatomic particles that we look at in chemistry: protons and neutrons, and they're in the nucleus, and electrons that are in an electron cloud. So in terms of the basic size of an atom, so atoms are of course extremely small. So the diameter of an atom is around 10 to the minus 10 meter. So about 10 nanometers. And the diameter of a nucleus is around 10 to the minus 15 meter. So that's a power, so 10 to the 5th power difference. So the electron cloud's about 100,000 times the size of the nucleus of an atom. So to put that into perspective, if the nucleus was the size of a golf ball, then the electron, so you all know about what a golf ball looks like, right? About the size of a golf ball. So if we scaled the nucleus up to the size of a golf ball, then the electron cloud would scale up to about 3 miles in diameter. So if you put a golf ball on this table and you went out 1.5 miles that way and 1.5 miles that way, the electrons could be anywhere in that space. So they can be way out there compared to the nucleus. Or as another perspective, if the nucleus, so if we scaled it up to the size of a pea, And we went to Dallas Cowboys football stadium, and we put that P on the 50-yard line. So if that P represented the size of the nucleus, then the electron cloud would be the stadium itself. So the electrons could be anywhere in that stadium except in the nucleus, because in the nucleus and the tiny, tiny P is what's in that is only the protons and neutrons. Okay, so the basic properties of the components of an atom. So if we look at their mass and their charge, so electron, of course, they're extremely small. Electron has a mass of 9.109 times 10 to the minus 31 kilograms. And a proton has a mass of 1.67262 times 10 to the minus 27 kilograms. So it's heavier than an electron, and a neutron is a little bit heavier than a proton, 1.67493 times 10 to the minus 27. But protons and neutrons have about this similar mass, but much more massive than an electron. So in terms of the relative mass, if we just compared the two, so if we took the mass of a proton and divided by the mass of an electron, then that's 1,836 if you divide those two numbers. So protons are about almost 2,000 times as massive as electrons are, and neutrons are a little bit more massive than protons are. So in terms of charge, so electrons have a charge of negative 1.60218 times 10 to the minus 19, and that would be units of Coulomb. And so the charge on a proton is same magnitude, but it's opposite sign, so 1.60218 times 10 to the minus 19 coulombs. And neutrons have no charge, they're neutral. So we'll look at a mass unit called atomic mass units in the next lecture. So one single electron has a mass of 0.00055 AMU, and one proton's 1.00728, and a neutron 1.00866 atomic mass units. So we won't be using these numbers for charge in this class. If you take a physics class, electricity and magnetism, you'll no doubt use those numbers. Most chemists just think of electrons in terms of being -1 charged, and protons as being +1 charge, and neutrons having no charge. Okay, so the majority by far of the mass of the atom is in the nucleus of an atom. So basically this would be the basic structure of an atom. So if the pink dots represent electrons, they're in the electron cloud, flying around really, really fast in the electron cloud. And then the red dots representing protons are in the nucleus, and the navy dots representing neutrons are in the nucleus. So you can think of the electrons then as orbiting the nucleus. So what keeps the electrons from just flying off into space? Well, one thing would be that there's an attraction here, right? So electrons are attracted to protons because one's positive and one's negative. And then also, because there's so much mass in the nucleus of the atom compared to the electron, you need to talk to a particle physicist about this, and probably there's some I would think there are some gravitational effects there as well. Okay, so nuclide symbols. So this is not drawing the picture is not a convenient way to represent what an atom looks like. One way to represent what an atom looks like is to draw what's called a nuclide symbol. So it's basically just a shorthand notation to represent how many protons, neutrons, and electrons an atom has. So this would be a nuclide symbol. So if I ask you to write a nuclide symbol, that's what I'm asking you to write. So it'll have a superscript, it'll have a subscript, and it'll have the element symbol. And it may or may not have a charge. So what is the superscript? So the superscript is what's called the mass number. Oops, I'll do that. So sometimes given the symbol A. So the mass number is simply the total number of nucleons in the nucleus. So it's the total number of protons and neutrons in the nucleus of the atom. And the subscript is what's called the atomic number, given the symbol Z, and that is the total number of protons in the nucleus of the atom. So how can you figure out how many neutrons there are? Well, since the superscript represents the total number of protons and neutrons, and the subscript represents the total number of protons, then you can subtract the two, and that tells you the number of neutrons in the nucleus. So there's 11 protons and 12 neutrons in the nucleus of that atom. So if we look at a periodic table, and so I've just shown a few elements here. So the number typically in the upper right hand corner, that is the atomic number. So that's the number of protons in the nucleus. So hydrogen has 1 proton, helium has 2 protons, sodium has 11 protons in its nucleus. So this would be, so the periodic table that we use at Anim Commerce, the nuclide, or the element symbol on the periodic table looks like that. So this upper right hand corner is the atomic number of protons. This number in the left hand corner is what's called electronegativity, and that's something we'll discuss several chapters for now. And the number at the bottom, this is something that confuses students all the time. That is not mass number, right? That is atomic mass. Totally different things, two totally different things. So mass number is a number of things. It's how many of something there are. In this case, how many protons and neutrons there are, right? There's 11 protons, 12 neutrons, so equals 23. The number at the bottom in the element symbol in the periodic table is the atomic mass. The atomic mass is how much something weighs, right? So it's not how many of something there are, which is mass number, it's how much something weighs. And we'll talk about atomic mass later. So don't get the two confused. Mass number and atomic mass is totally different. Okay, so given the nuclide symbol like that, then 23 is nucleons, 11 protons. Again, we subtract the 2 and get 12. That's the number of neutrons. So now how do you figure out how many electrons there are? You figure that out. Number of electrons is figured out by what is here. And in this case, there is nothing there. So usually, so there may be a charge there, like +1 or +2 or -2 or -3, or there may be nothing there, which means the charge is neutral on the atom. So how can it be neutral if protons are positive? So if you have 11 protons, those are positive. And then we add the number of electrons, which are negative. And in this case, it equals 0 because there's nothing there. Then the number of protons and electrons has to be equal. So you have 11 positives, right? 11 positives, 11 negatives, and they cancel each other out, so there's no net charge. So if there was a positive number here, then that would mean there's more protons than electrons, right? If there was a negative number there in the upper right-hand corner superscript, then that would mean there's more electrons than there are protons, and we'll see examples to illustrate that. Okay, so if we sketch what this atom looked like, so we have a nucleus that's got 11 protons in it, and it's got 12 neutrons in it, and it's got 11 electrons in it circulating around the nucleus. Okay, so what's the number of protons? That determines what the element is. So every single sodium in the entire universe has 11 protons in its nucleus. If it has a different number of protons, it's not sodium, it's some other element, right? So if we looked at the periodic table, so every single helium atom in the universe has 2 protons in its nucleus. So atoms can have different numbers of neutrons and electrons and still be the same element, but not different numbers of protons. So every single hydrogen in the universe has 1 proton in its nucleus, right? Every single sodium has 11 protons in its nucleus, but they can have different numbers of neutrons and electrons. Okay, so how about if we take this nuclide symbol? So now how many protons, neutrons, and electrons does it have? So still it has 11 protons. All right, we subtract the 2, 12, so it's got 12 neutrons. Now how many electrons does it have? So now we look at this, now it's plus, it's positive. So we have 11 protons that are positive. And then if we add the number of electrons that are negative, it must equal +1. So if we have 11 positives, then we only have 10 negatives. Right? And so if we add 11 positive and 10 negative, we get a net +1 left over. So there must be 10 electrons. Right? So if the atom has a positive charge, again, it has more protons than electrons. However many positives it has, that's how many more protons it has than electrons. So an atom with a net charge is called an ion, so some terms for you to know. And if it's positively charged, then that ion is called a cation. So this will be one way that you know if you're talking to a chemist or not, because if you're not talking to a chemist, how would a non-chemist pronounce that? Probably cation, right? But that's not cation, it's cation. So that's how a chemist would pronounce that. So a cation is any atom that's got more protons than electrons, therefore it's positively charged. Okay, so if we take these, how many protons, neutrons, and electrons does each have? So 20 protons, and we subtract the 2, so 20 neutrons, and there is no charge here, so there must be 20 electrons, right? If there's no charge, then it's got the same number of protons and electrons. That way the positives and the negatives cancel each other out. Or if we take this, so 20 protons, subtract the 2, so this has 24 neutrons in the nucleus. And now it's got a +2 charge, so there can only be 18 electrons, right? So it's got 20 protons that are positive and 18 electrons that are negative, and if you add those two together, 20 positives and 18 negatives gives you 2 positive net, right? So if we sketch what those atoms look like, then it's got 20 protons, 20 neutrons, and 20 electrons. And this would have 20 protons, 24 neutrons, and 18 electrons, right? So it's got more positives than it has negatives. And it's got 2 more. Okay, so if we take these two, so 16 protons, and if we subtract those 2, so that's 8, and that would be 18, right? So it's got 18 neutrons, and there's nothing here, so it's got to have the same number of protons and electrons, so that those two numbers cancel each other out to 0. Or in this case, if we subtract those 2, so 16 protons, 18 neutrons, but now it's -2 charge, so now it's got to have more electrons than it has protons. So it has 16 protons, so it has to have 18 electrons, right? Because 16 protons that are positive and 18 electrons that are negative, and if you add those two together, then you get a -2, right? So that means, so if this is negative, it's got more electrons than protons. So again, if we sketch what those atoms look like, so 16 protons, 18 neutrons, and 16 electrons, and this will have 16 protons, 18 neutrons, and what did we say, 18 electrons. Right, so again, the number of protons to electrons gives you the charge on the thing. So an atom with a net charge, again, is called an ion. And if it's negatively charged, as it is in this case, then it's called an anion. So an anion is a negatively charged ion. It's got more electrons than protons. Okay, so let's sketch these 3. So these are all variations of hydrogen. So sometimes you see it wrote like this. So this is the nuclide symbol, or sometimes you see it wrote like hydrogen-1, hydrogen-1, and that number is the mass number. So this would be wrote hydrogen-2 and hydrogen-3. So hydrogen-2 is sometimes called deuterium, given the symbol D, and hydrogen-3 is sometimes called tritium, given the symbol T. So if you look at a periodic table, there is no D and there is no T. An element symbol that says D or an element symbol that just says T on it. Why not? Because they're all variations of hydrogen, so they're all taken care of by that right there. Okay, so if we sketch what these look like, so the charge on each of them is 0, so no charge, so they have to have the same number of protons and electrons. So the subscript is 1, so they all have 1 proton. So this has 1 proton, and if we subtract that, it has no neutrons and 1 electron. right? And in this atom would have 1 proton and 1 neutron, so if we subtract these two, we get 1, so 1 proton, 1 neutron, and 1 electron. And this atom of hydrogen has 1 proton, 2 neutrons, and 1 electron, right? So 3 minus 1 is equal to 2, so 1 proton, 2 neutrons, and 1 electron. So they're all variations of hydrogen, but they only differ in the number of neutrons, right? This has no neutron, this has 1 neutron, this has 2 neutron, but the number of protons and electrons is the same. So atoms that only differ in the number of neutrons in their nucleus are said to be isotopes of each other. So another term for you to know. So all of these occur in nature, but they all don't occur to equal amounts. So you don't get a 33% of each one in nature. So what you find in nature is that most hydrogen in nature looks like this. 99.985% of hydrogen in nature has no neutrons in the nucleus. Right? 0.015% of hydrogen in nature has one neutron in its nucleus. And it's a perfectly stable nucleus. It's deuterium. We have deuterium in my research lab, right? Perfectly stable, perfectly fine to work with. But tritium, however, so you only find trace amounts of this in nature, and it is not stable. It is radioactive. So it does not have a stable nucleus, so it'll undergo a nuclear reaction to achieve a stable nucleus. Okay, so some elements only come as one isotope in nature. So for example, fluorine only comes as fluorine-19 in nature, 9 protons, 10 neutrons, 9 electrons. Every single fluorine in nature has 9 protons, 10 neutrons, and 9 electrons. Every single sodium atom in nature has 11 protons, 12 neutrons, and 11 electrons. Right? Only one isotope. Calcium, however, has 6 different isotopes in nature. Oxygen has 3 different isotopes in nature. Some oxygen 16, oxygen 17, oxygen 18, right? So each element is different. Okay, so just to say a little bit more about this, so in which, you know, what leads to something being radioactive, so would be an unstable nucleus. So if the proton to neutron ratio, which is what's in the nucleus, gets out of whack, then the nucleus can be unstable and it will undergo radioactive decay to create a more stable nucleus. Basically, when that happens, protons are if you have too few neutrons, then a proton can be converted to a neutron. Or if you have too many neutrons, then a neutron can be converted to a proton. So for the lighter elements, usually you have about a 1-to-1 ratio of protons to neutrons. As the element gets heavier and you have a lot of protons in the nucleus, then generally you need more neutrons to stabilize that nucleus, and you would have more neutrons than protons in the nucleus. But we're not going to say much about radioactivity in this course. Gen Chem 2 will cover an entire chapter over the nucleus of an atom and radioactive decay. Okay. So let's take a few more examples. So how many protons? How many protons, neutrons, and electrons does this have? So iron, Fe is iron plus 2, has a plus 2 charge. So this is a little trickier, right? Because you're, I didn't give you the subscript. So how do you know how many protons it has? Well, you'll have a periodic table for the test, or in my case, my phone, but I'm using my phone to record this. I have a periodic table on my phone, so everybody has a periodic table on their phone, right? If not, you should get one, just because it's the cool thing to do. Okay, so let's take these two. So iron 56 and nitrogen 14, and so iron has a 2+ charge. So how many protons, neutrons, and electrons does it have? So this is a little bit harder because I did not tell you how many protons it has. So how are you going to figure that out? So you have to look on the periodic table, right? So I'll email you a periodic table that you can use for this class. Or if you're like me, should have a periodic table app on your phone, right? Because that's just the cool thing to do. So if you have a periodic table, you can look on the periodic table. And if you look up iron on the periodic table, then iron is atomic number 26. So this is going to have 26 protons since it's atomic number 26. Again, so that would be if you look at the entry for iron on the periodic table, right, in this upper right hand corner, number 26, that's its atomic number, which is number of protons. So 26 protons, 30 neutrons, and now it's got a +2 charge, so it's got to have 2 more protons than electrons, so it's got to have 24 electrons, right? And then nitrogen 14 with a 3 negative charge. So if we subtract these two, so this is the number of protons, this is the number of neutrons, so 7 protons, 7 neutrons, and then it's got a 3 negative charge. So it's got to have 3 more electrons than it has protons, right? Since these are positive and these are negative, and if you added those two together, you would get 3 negative. Okay, and if we did these, took these 3, so if we subtract these, 10, so 9 protons, 10 neutrons, it's negative charge, so it's got to have 1 more electron than proton, right? 9 positives, 10 negatives, so net -1. Subtract these two, so 10 protons from that number, 10 neutrons from that number. It has no charge, so it's got to have the same number of electrons as it has protons, right? Those have to be the same. And in this one, so 11 protons, 12 neutrons. It's got a positive charge, so it's got to have 1 more proton than electron. Okay, so I did this example because these all 3 have 10 electrons, right? So if we sketch what these atoms look like, so the 9 protons, 10 neutrons, 10 electrons. This has 10 protons, 10 neutrons, 10 electrons. This has 11 protons, 12 neutrons, 10 electrons. So all of these have the same number of electrons. So there's a word for that. So atoms that have the same number of electrons are said to be isoelectronic with each other. Okay, so lots of terminology for you to know in this chapter. And we'll stop there.